Welcome everyone to this Introduction to FeatureCAM demonstration. In today's demonstration, we're going to be seeing how FeatureCAM really is a complete manufacturing solution in the subtractive space. In today's presentation, I'm going to start with just a basic introduction to kind of the whole idea of our demonstration today, as well as myself. And then we're going to be jumping, almost all of this presentation is going to be actually in software demonstrations. We're going to be machining a bunch of different components utilizing a wide range of machines and different processes that we can to come up with an overall assembly. And we'll start with some FeatureCAM 2.5D, continue that along, transitioning into 5-axis positional using some of that same information that we've covered. We'll take a look at some surface milling, some 3D surface milling within FeatureCAM, and then finally some traditional lathe turning and live tooling, turn mill type operations, and finally some Wire-EDM. So my name's Kelby Oki. I'm a senior implementation consultant specializing in FeatureCAM. Now, originally I studied mechanical engineering at the University of Utah before I started working as an applications engineer at the time, Delcam, which of course was acquired by and we all transitioned into being Autodesk applications engineers. In my 5 years at Autodesk, I've done pretty much everything when it comes to FeatureCAM and even some of our other products, from supporting to training, consulting, demonstrations, and actually one of my biggest focuses has been developing training content for both our in-person training classes, things like that, as well as all of the online training content and platforms that we've used. Okay, so here's the idea with today's demonstration. Now, today's demonstration, it's really meant to be just that, an overall wide viewing demonstration of the wide range of capabilities that FeatureCAM has. So less of a training, click here type of session, and more of a demonstration of the capabilities. And we're going to be looking at the example of a steering wheel assembly. I think this was pulled off of I think it was called the Bloodhound project, something like that, in which we helped manufacture a bunch of components for a car to try to break a land speed record, actually here in my home state of Utah, out on the Bonneville Salt Flats. And it's pretty cool. So we've taken a steering wheel assembly here, and it's a particularly good example. There are a lot of components here. We won't be looking at every single component today, but it really breaks down nicely into the different types of documents and machines that FeatureCAM can program. So we'll look at various components of this overall assembly and manufacture them. So for this example, our factory, we have a wide variety of machines available to us. We've got a basic 3-axis mill in a Haas VF4. This obviously could be substituted for any 3-axis mill. We have a 5-axis machine, in this case a Hermel C30, a Mazak Integrex. This is going to be a pretty complex lathe with live tooling that we can work with one of our components. And then we have a Sodic 4-axis Wire-EDM machine that we'll be using for our final component in our final operation. The components we're going to be machining today will start off by doing this top mounting plate of our assembly, utilizing 2.5D milling. And we have a wheel hub plate, a steering wheel mold, and a steering wheel boss. So 4 components in total with, I think, 6 operations machining these. So with that, let's just jump straight into it. We have a whole lot of information to cover today, so we're going to jump straight into our first component, the top mounting plate. For this first part, we'll be machining the top mounting plate part of our overall steering wheel assembly. We'll be machining this part out of aluminum, and we'll be using our Haas VF4, so just a pretty standard 3-axis mill. Now, as we have this part open, you'll notice that there are 2 different setups. The idea here is that with setup 1, we'll be holding onto our stock with a vise and just facing and drilling all the holes on this part, which will allow us for setup 2 to kind of use these holes as an option to bolt down our part so that we can then mill the outside of our profile here, which we normally wouldn't be able to do if we were hanging on to it with a vise. So to start out, I'm going to open up stock 1, and we'll just make sure that under material, it looks like we are set to aluminum. So this will drive the appropriate feeds and speeds to machine this part. And with that, let's recognize the features off of this part. We're going to utilize automatic feature recognition, or AFR. This allows us to basically state that we want to automatically recognize features relative to both setups 1 and 2 directly off of this model. So as I hit next, you can see FeatureCAM very quickly scans the entire model. And with this first setup, I'm going to deselect sides 1 and 2 because remember, we really just want to do the drilling with this kind of vice setup, as well as we can face the top. And then if I press next, setup 2, even though it's in the same location, it's not like we're flip machining here, I can do the inverse. I'm going to shift select all these holes and faces that we've already machined to this point. No, that shift select tip didn't work on this one, that's fine. And then we'll be just left with the side features, which takes care of the milling around the outside that we wanted to do. So that's it for the most part with our programming. We hit finish and all of the features are created for us. These holes are similar, so they've been grouped into a pattern. Then we have a different sized hole followed by our milling features. Now, before we run a simulation, I do want to deburr this part. So for these holes, the easiest way to do this is simply going to be to add a chamfer to the top of this hole. As I hit apply, FeatureCAM creates the necessary chamfer operation. And I can then go do the same with this other hole. That's the power of having hole patterns for similar holes, is I only needed to make that change once for the entire pattern as opposed to 4 different times. Now, looking at setup 2, this side feature runs around the entire top face of our part. Therefore, this is a pretty good candidate to add a chamfer as well, just to chamfer that top edge. However, if we look lower on the part with side 2, adding a chamfer here is going to skim around the entire part. Not necessarily what we want. So for this one, I'm going to use FeatureCAM's IFR technique to manually, or still pretty automatically, extract chamfer features from this model. We're going to go with that same size and only select just kind of this lower open face that we want to chamfer. Hit finish. And FeatureCAM has created what I like to think of as a smart chamfer operation here, in that it is a 3D chamfer with check surfaces. So all of these surfaces that it's recognized, FeatureCAM is going to keep the tool from running into, which is pretty handy. So with that, we're ready to run a simulation, which will generate our NC code to machine this part and put it on the machine. Start with setup 1, running a 3D simulation. And I do want to make sure that I have cut higher operations, just to make sure that we're doing the higher and the Z operations first and not colliding anything down the road. I'm going to hit play. We can see our first face, followed by the drilling, and then chamfering those holes. Now, if I move to setup 2, we'll see the work holding in our graphics window update. Oh, looks like I had an error. I think that's associated with the tooling. Totally omitted selecting the complete solution demo tooling database. This is just a little database I put together beforehand to machine all of these parts we'll see in this demo. It's going to allow me to quickly run through setup 1 again. Face, drill, chamfer. And then select setup 2. We'll see our work holding update. No error this time. Exactly what we want. You can see what we were going for here. And now we're just kind of bolting our part down using those holes that we drilled previously. And we can handle all of the milling. Looks like we chamfered that beforehand. We could change that operation order if we want, or if we're happy with this, that's totally fine as well. So with that, we've completely programmed the first part for this assembly. Again, using just a standard 3-axis mill, we've used automatic feature recognition to recognize all the features here, and we're ready to start machining. The next component that we'll be manufacturing as a part of our overall steering assembly is this wheel plate hub. Now, we're going to approach this with 2 different operations. This first one, we'll be machining it, just this top face, this pretty basic setup, just on our 3-axis mill, in our case, our Haas VF4. And we'll be machining this part out of aluminum. We'll then, later on, go to machine the rest of this part on our 5-axis machine using 3+2 machining strategies. So as a first step, I'm going to open up the stock and ensure that, it looks like we're using aluminum right now. So I'm going to change the default material, looking at our list of defaults, to titanium, which will make sure that we're using the appropriate feeds and speeds once we've programmed our features. Now, for this example, we won't be using automatic feature recognition, but instead, I'm going to use a combination of just features from dimensions and interactive feature recognition to program this part. Now, if I take a front view for this face feature, you'll notice that our work offset, or our setup, is placed on the front face of the part, not the stock, meaning that we can just locate this face feature at =0 and hit finish. Next, we'll do the holes. Utilizing feature recognition, we'll check extract with feature recognition. Next. And we can see that FeatureCAM recognizes all of the holes we'll need for this given setup. The only thing I'm seeing here is that it has split these two holes into two separate ones, but no matter, we'll just change the depth of this first one. So we'll select that. We want these all to be created, and we'll just select it to machine deeper to cover this bottom portion. So I'll open this hole pattern. And again, this is really helpful, just the power of hole patterns here. We have two holes, but we only need to make this change once. You'll notice depth is in blue, which allows us to pick the depth exactly off the model. So we'll say, let's go from that top face down to this bottom face. And there we go. I like that update. Now we'll just run a quick 3D simulation. We can see we face our part and then drill each of the holes. Now, one thing you'll notice is that we haven't taken work holding into account. I want to use this as an opportunity to show off one of the default add-ins in FeatureCAM, and that is the Import Vice add-in. You'll find it in this add-in library titled Import Vice. With that, you can load it and then run it. Selecting one of FeatureCAM's default vices, we want this positioned in the center along the X. You can import this entire model to be used for our simulations. Now we can run a much more intelligent 3D simulation, ensuring that we're not running into any component of our vice. You'll notice that a part of that import vice add-in included not only bringing in and aligning each one of these individual solids, but setting them as a clamp, ensuring that if we run into it, we will know in the 3D simulation. Awesome. This looks safe. We have our first setup ready to be machined. I'm just going to save our simulation results as an STL just on my desktop. And we'll use this as the basis for our stock once we move on to the 3+2 machining of this part, so that we're having the most efficient process that we can. We're going to continue the machining of our wheel hub plate. Previously, we did our first operation on just our Haas VF4, simply facing and drilling the holes on what we can now see as the bottom side of our part. And now you can see we have a part here where we have imported some fixture solids to hang on to our part and make sure through simulation that we're not gouging anything. I've selected these as clamps. And you can also see that I've brought in that STL that we saved out to be used as our stock in this case. This will make sure that we don't end up machining anything that we already have. So I'll open up stock 1. You can see right now we just have that block stock. So instead I'm going to jump to user defined, stock solid, and I'm going to select that STL. Additionally, it looks like we have aluminum selected again. I'll go ahead and change that to titanium. Now we can see our stock's updated, not only for the overall block shape, but it's including these holes now, which is exactly what we want. So now for the programming of this 5-axis positional or 3+2 part. You'll notice that we have multiple setups here. Each one of these is necessary in a 3+2 part to essentially define the tool axis for a given feature. So in this case, we'd really just have 3 setups. Everything we do from the side setup. Then what we're referencing is the top from this orientation, and then that back setup. Once we have these created, it's as simple as looking at each one of these setups almost as if it were its own 2.5D part. So I'll select, we'll start here. Let's start by recognizing the holes, very similar to how we've done up to this point. We want everything along the setup Z for this given orientation. And we can take a look at the holes FeatureCAM found. And those all look great to me. I'll hit select all, finish. And from this orientation or this setup, we have all of our holes created. Next, I'm going to take a look at side features, see what of these profiles we can mill with a side feature. We'll use extract with feature recognition. And I'm going to use this automatic option. This is not to be confused with automatic feature recognition. This instead is specifically dictating we want side features created and recognizing them off of the model. I like these two. We definitely want to be machining those, and a side feature seems appropriate. It also looks like it's gotten this outer profile. And we'll leave it at that for this setup. I think finally I'll just throw a face at Z equals 0 here to machine down to that front face. And we have our first orientation, I believe, fully programmed. From here on out, it's just rinse and repeat with each one of the additional orientations. And that's really all there is to 3+2 machining. Now, in the interest of time, I'm going to do my best Bobby Flay impersonation, a little TV magic where we pull the quiche out of the oven already cooked and skip ahead to this completely programmed part. We're just doing the same thing, going to each setup, creating additional features until ultimately we end up with a feature-rich part in each setup. We can see that most of it, same stuff we did in that setup 1, already taken care of. And then additionally, we had a side feature and a hole pattern for this top setup, and then just a face on the back. So now with our STL defining our stock, our fixtures included, and all of our orientations programs for this 5-axis positional or 3+2 part, we can run a simulation. I'll switch this to 3D to see what we're left with. So awesome. With that, we completely machined this component using 2 different setups and 2 different machines, which is pretty cool. We started on our Haas VF4, just machining this bottom face so that we had something to hang on to for our 5th axis setup. And not only that, we were able to save our simulation results as an STL, ensuring that further operations didn't end up creating any tool path that would result in air cutting for this secondary operation on our 5-axis Hermel C30 machine. It looks like we're safe, and we have a completely machined component. For this next part, we're going to continue the manufacturing of our overall steering wheel assembly by looking at the actual steering wheel mold. So the idea here is that we'll machine this mold, and then we'll use it for the carbon layup process to make this steering wheel. Now looking at this, you're going to notice that it differs significantly from the parts that we've seen up to this point, in that it can't simply be described by FeatureCAM's 2.5D features. There's no real holes here. Maybe some stuff that we'll end up cutting with sides. I suppose we could face it. Definitely no pockets or bosses. We're going to have to utilize FeatureCAM's surface milling strategies to cut these more free-form surfaces. Now, we're going to be machining this out of tool steel. So as a first step, I do want to open up the stock. And I've already selected it here, but make sure to select tool steel H13 so that we have appropriate cutting data, feeds and speeds calculated for the machining of our part. We're going to start by roughing this material out so that later we can come in with ball end mills or whatever end mills we want and safely finish this part down to the part surfaces. So to do that, I'm going to take this view here. I actually don't want to touch these top surfaces, so I'll deselect those. Open up the new feature wizard and create a surface milling feature. Now, because we pre-selected these faces, they've all come in accordingly. I can step through the wizard and select the desired Z-level roughing strategy. So the idea here is that we're going to be machining this cavity, stepping down in Z at a given increment until we get not quite to the part surfaces, but close enough that we're then comfortable bringing in our finishing tools. I'm going to classify this as the 3D pocket. That's just going to allow FeatureCAM to ramp in as opposed to trying to enter in from the outside, which we can't do here. And then I'm going to grab, I want to use this roughing tool, this bull nose 8mm with a 1.5 mm tip radius tool. Finish, and awesome. We have our Z-level roughing strategy. Now it's going to take a minute to calculate. I do know the changes I want to make to this, so I'm not going to run a preview just for the sake of time here. I'm going to jump into the Z level, and you know what, that actually all looks good, other than in the dimensions. Even though we didn't select these top surfaces as part surfaces, I really want to make sure we don't touch them. So I'm going to utilize a tool called check surfaces. What these allow us to do is to not only say, because we didn't select these previously, we can very, very specifically dictate, do not touch these given surfaces when machining. So we know exactly what we're getting here. And then finally, if I jump to the roughing milling, I want to get this Z increment fairly tight at 2 mm. Awesome. So we have our part roughed out, and let's start looking at finishing. And I'm going to zoom in on this kind of, we have some purple and some pink surfaces here. And as we see this set of surfaces, I actually think the easiest way to machine these is going to be using a 2.5D feature, a side feature. Since we have this vertical wall, it's going to be easy enough to define it off of that. And then we can just add a bottom radius as a part of the side feature. So I'm going to use a cool tool here. I'm going to select this purple surface. And with this select drop down, we have the option to select every face on this feature, on this part by a color. And there's actually some other options here as well. Because I pre-selected that purple surface, it's grabbed that. So if I hit OK, I want to select everything with that color that is a solid. We can see it selects all of those surfaces going around the center part of the steering wheel mold. So with that, I'm going to open up the new feature dialog, extract some side features off of side surfaces, and here we can start to see that highlight of what we're about to create. We'll make sure that the machining side is correct. That one looks like it's off. I'll reverse it. Okay, that looks good. We're going to overwrite this bottom to go to this bottom face because it's just using those vertical surfaces right now. As I hit that, you can see it updates. There we go. We want to go all the way to the bottom here. And then finally, we're just going to add this bottom radius. Now, I don't quite know what this is, so I'm going to utilize the curvature tool in the geometry tools. If I just select this face, I'll notice in the bottom there, it says 1.5 millimeter radius. So it's just as easy as entering that here. Awesome. That's exactly what we want. So I'll just jump to the strategies. We don't really want to rough here. We already handled that with our Z level. And I don't want to ramp from the top, but I am going to indicate that we want to finish the bottom here. So with that, I'll hit next. We'll see the tools that it's using. That looks great to me. Finish. And we have our side milling feature here. I'll quickly preview the toolpath results. Awesome. So now that we have everything roughed out and the central part taken care of, let's start to look at some of these more freeform surfaces that are going to require some surface milling finishing strategies. We'll start by selecting these yellow surfaces. Again, I'm going to use that select by color tool. Pre-selected. Now I hit OK and select each one of those. I can create a new feature, and we're going to go with a 3D spiral operation here from the surface milling strategies. I want this to be a continuous step down, so we're just kind of spiraling down in. We're going to use the toolpath smoothing options and indicate that we don't want to roll over these edges at all. We just want to cut these yellow surfaces. With that, I'm going to hit finish. Jump to the tools to see what tools we're using here. 8mm, I want to reduce that just slightly, grabbing a 6mm ball end mill. I'll apply that change. And then if I jump to the milling tab, right now we have a pretty coarse step over at 1.25. I'm just going to preview this real quick so we can take a look at what that's going to look like with our ball end mill. And yeah, so I like the toolpath here, but I'm just going to reduce that step over a bit. 1.25 mm isn't the greatest surface finish. I'll get maybe 0.5 millimeter there. And I'm not going to preview it right now just because of the calculation time. I'm going to start and turn my gaze over now to these blue surfaces. So this is one surface. We don't need to do the select by color type option again. I'm just going to select that, and we could get away with a 3D spiral, but I want to use this as an opportunity to use probably my personal favorite strategy, and that's isoline. What this does is it's going to have the tool follow the contours of these surfaces exactly. So it's a pretty nice toolpath result. Same changes. I'm going to not roll over the edge at all. I'm going to use that same 6mm ball end mill. And then we'll just reduce that step over. We know what the default 1.25 mm looks like. Let's just match our yellow surfaces and go with a 0.5 millimeter step over. Awesome. So I'm going to run what's called a 3D rapid cut simulation. It's a bit quicker. We still have to calculate the toolpath, but it's essentially going to jump to the very end so we can see our toolpath results rather than seeing the tool remove material throughout the entire machining process. And here we can see our results. They look really, really good. The only thing that I see here, and you're going to notice some fragmentation just due to my graphics card, I do see that it kind of looks like we're not hitting in these corners very well. You can really see the fragmentation when I zoom in. So I do want to utilize what's called a corner remachining strategy just to clean up any of these tight bottom radius areas. They were really only in these yellow sections. So I'm actually going to grab this selection from Surface Mill 2 where we already have those surfaces selected. And I'm just going to add a new process or operation and add a corner remachining operation here. Now, this is what I like to call a smart toolpath. I can jump in and essentially state that previously we used a 6mm ball nose end mill and hit OK. And FeatureCAM is going to scan these surfaces and say, where could we not get into with a 6mm ball end mill? And let's put toolpath there based on our new tool size that we're using. In this case, we're going to grab just a 4mm ball end mill should do it. I'm going to jump to the milling, and it looks like we have a pretty tight scallop height here. I'm going to reduce that just for simulation purposes. So this looks, well, we'll just keep it right there and run a final 3D simulation to look at our final tool mold results for the steering wheel. And here we can see our final part quality. We have excellent results, and we're ready to move on to the next component. For the final component that we'll be machining for this steering wheel assembly, we have the steering wheel boss left. Now, very similar to the wheel hub plate that we created, we're going to do this using two different operations. The first of which, we're going to use a turn mill style setup using our Mazak Integrex to do both some lathe work and some live tooling work to get a near net shape here. And then finally, the second operation is going to be on a Wire-EDM machine in which we cut out this middle area that is particularly well suited for the strengths of our Wire-EDM machine. So let's just jump straight into the programming of our first turning feature, and that is going to be facing off this front edge. I'll open up the new feature wizard. This is going to be a turning style face feature, not a live tooling. I'll select face. We just want this located at that z equals 0. It's pulled an appropriate OD and thickness for us. We can just hit finish and we have our face feature created. Next, I want to turn the overall profile here, of course, minus these flats. And before we do that, we're going to have to generate a profile or a curve to describe our 2D lathe style operation. So I'm going to open up the curve wizard, and we have a tool called revolved boundary that's going to allow us to just pull profiles straight off of this model. So here you can kind of see where we're headed. If I select finish, and I'm actually going to just hide the solid for a moment, take a top view and zoom in. Here we can see the profile. I'm going to delete this stuff we don't need. We have a profile that we can chain into a curve and use to describe our OD turning operation. And create a new feature, again, a turning feature. We'll be turning it from that curve that we just created. You can see a preview of that. I like the tooling that it's picked, so we can simply press finish. We'll run a quick 3D simulation to see where we're at this point. Awesome, that looks pretty good. Now let's take care of, I'm going to show the solid here again. I want to do a little bit of an on-center drill here, just to make it a little bit easier when we're doing our Wire-EDM operation. We'll have a nice little pre-drilled location there. So I'm just going to create a new feature. Now technically this could be a turn mill or a turning. Since it's on center, I'm going to do a turning hole feature where our part is rotating and our tool is stationary. I'm going to give it a depth of 55 and a diameter of 12. And preview that. Looks good. We'll just hit finish. And with that, we've done pretty much all of the turning operations here. We can start to take a look at some live tooling operations. Awesome. So let's first take a look at this flat here. I want to hit this using live tooling around the index axis. So I'll create a new feature and this time select turn mill. As I hit next, we're going to see the same 2.5D features we've seen up to this point, indicating that we're now programming live tooling features, not traditional lathe features. This is going to be a side feature, and we don't want it along the setup Z. We want our tool coming in from the index axis. So to figure out exactly what angle that is, I'll select normal to this surface. We can kind of see our tool axis updated here with this blue preview, our Z pointed up. That's what we want. I'm going to see if automatic recognition will grab. Yeah, it looks like it's grabbed this side feature. It's even included the bottom radius. It's exactly what we want. So with that, we can just hit finish. I'm just accepting the tooling. It's selected here. It looks pretty standard. I'm okay with that for this part. We'll press play and we can see we now have that flat machined. Now, the rest of these flats here, this is so long that I'd actually rather approach this from the sub spindle. And we'll actually notice that we have some chamfers on the back side of these holes. Those are definitely going to be easier to reach on the back side from a sub spindle. So next, I want to cut this part off and transfer it to the sub. There's a feature in FeatureCAM called a cutoff feature. It's going to make this particularly easy. It's going to be a turning feature because it will be our part rotating here, not live tooling. And we'll find cutoff in the from dimensions section. Now it's pulled the OD and the ID from the part. We'll leave those in the width. Those all look fine as default. However, I do want to make sure to check that we will be transferring to our sub spindle. Based on how our post is set up, this will come up with all the right NC code for your given machine to transfer to the sub spindle. And I even have the option to indicate a few specific parameters here. How much do we want to grab onto? Well, I'm going to do a quick measurements. I'll just use the dimension tool just to get a ballpark. 40, okay, well, maybe we'll say we'll grab onto roughly 40 millimeters. Hit escape one too many times. We'll say we'll grab onto roughly 40. Place the location of this cutoff feature on this back edge. And we can hit finish, and we have our cutoff feature. Now I've already created a setup on the back side here. It's worth noting that if I double click on this to open it up, that this setup has been associated with the sub spindle. So we've gone through and done all of our main spindle operations. We have our cutoff that includes a transfer to the sub. And now I want to make sure to click setup 2 to activate it. We can program features that will be associated with our sub spindle. Let's mill these flats here. I'm going to use a side feature for that. Turn mill because we're live tooling. Side feature extracted with feature recognition. And I actually want this one along the setup Z this time so that the side of our tool is on these flats. It looks like Automatic did a good job of finding this, so we'll just simply select it, finish. And I'm actually going to extend the depth just slightly so that we're overhanging our tool. We'll just add a millimeter, making it a total of 6. Awesome. The only thing we have remaining are these holes. Simple enough. Do new feature. These cannot be turning. These have to be live tooling since they're off center. We'll go hole, pull those from the model with feature recognition. We are along the setup Z here. FeatureCAM found them just fine. We'll select 1, 2, 3. Finish. And we'll run a final 3D simulation to take a look at the result. Awesome. So we have the first operation done on our part, and we're ready to move on to the next operation on our Wire-EDM machine. So moving on to the second operation of the steering wheel boss, we have our resultant, which we've actually saved out the simulation results from that previous part as an STL, giving us our resultant stock for this Op2 on our Wire-EDM machine, in which we'll be cutting out this internal profile that is particularly well suited for a Wire-EDM operation. So first, you're going to see that the stock, we just have a round stock here, and we've brought in this STL, so let's utilize it. We'll open up the stock properties and say that we want to do a user-defined stock using, what's the name of that? Turn stock, our STL. Okay, and apply. And here we can now see that same resultant, that same output from our first operation of this part. Now, you're going to notice that the preview of the stock, or what we're seeing, we see all this triangulation data because it's an STL. It doesn't look particularly great. So I'm just going to quickly jump into the options. And in our, I believe it's the simulation, no, it might be display shaded. We're going to shade our stock with just that default opacity. I'll hide the STL so we can get a better idea of what's going on here. And there we go. We can see right there, we have our pre-drilled hole, and we just want to use our Wire-EDM machine to get this internal profile. So let's just jump straight into it. I'm going to open up the new feature wizard, and because we're in a Wire-EDM document, we're seeing some new feature types here that we haven't seen up to this point. Now this is a 4th axis, didn't mention, and I actually need to grab my post at this point. We're gonna use a SODIC. It's a 4-axis, although we'll just be doing 2-axis Wire-EDM feature here. And we're gonna use a die feature. Now think of this just like the pocket feature in a normal 2.5D document. Alternatively, there's punch, which is very similar to a boss feature, sides, which is just like a side feature. And then we have rapid options for this Wire-EDM document type. So this is the solid that we want to use. I'll hit next, and it jumps us straight into a mode where we can essentially chain what we want. We want this internal profile, so I'll select that, and next. And then it's just like defining any sort of milling feature. We don't want to offset the top, but we do want to change the thickness to go all the way through this part. So top face down to bottom face, if I recall, that should be 55. Yeah, we have it right there. I can press next. And now we need to define where exactly we want to start this. So I want to use a perpendicular lead. So if I select that, I can then basically state that we want to start in the middle and go perpendicular to this segment here. That's how we'll essentially start into the machining of this. Now we have a few more settings to set here. Retract here means that we're going to be removing all of the material from inside this component. We'll leave that. And I want to reduce the retract length to 1 millimeter. And you'll see what this does here in a second. Basically, we don't want to retract to the center region, or the material is just going to fall off before we've actually cut off. Then with this stop length, I'm going to reduce this to 5 millimeters so that we're stopping on this straight edge here. So with that, we can hit next. We have our operations created. I'll hit finish. And we'll just run a 3D simulation. I'll slow it all the way down so we can really see what's going on here. And we can see our retract there, where we're not fully cutting it off until we come in and we have that 5 millimeter stop. And I'll just use this select tool. We can select these components that have been cut just to get rid of them in this preview. And there we have our fully eroded part using our Wire-EDM machine to obtain this inner profile. So as you can see, Wire-EDM is actually pretty straightforward. And with that, we have successfully completed the 6 operations necessary to complete our 4 different components. We started with our top mounting plate, in which we utilized FeatureCAM's automatic feature recognition. We then moved on to a 2-op part with our wheel hub plate, in which, again, we just used that same 2.5D feature recognition, that time using interactive feature recognition, but then added on to that an additional operation in which we used 5-axis positional machining, very similar to our 2.5D process, with the added step of having various setups defining our different tool axes for 5-axis positional machining. We changed gears a bit and then jumped into our steering wheel mold, in which we took somewhat of a deep dive into our surface milling strategies, in which we can use those to create these more free-form surfaces like we had in that part. And then finally, we had our 2-op part for our steering wheel boss. We started by using some traditional, just pretty basic 2-axis lathe type operations, layering some live tooling operations with our integrex on top of that, and then finally doing a second operation using our Wire-EDM machine to get this final inner profile. So with that, we've machined most of the components for our steering wheel assembly, and hopefully along the way, you've gotten a pretty good idea of how FeatureCAM is a very powerful tool that can program a wide variety of different machines or parts in your shop as well. I hope this demonstration was informative, and with that, I want to thank everyone for your time.